Very good. Well, good afternoon. It's at least afternoon here in Denmark. So, Torben, Bonde, and I are happy to present this or make this presentation for you about straw briquettes, which is a second generation raw material that can boost your biogas production and then replace other raw materials such as silage. Torben and I have worked for this for several years. So Torben as a biofuel specialist and me on the mechanical side, the briquetting part. But let's see if we can. Here we go. Sorry. Now, when we talk about second generation, what do we really mean? I mean, most people know what first and second generation is, but just to repeat, a lot of companies use corn silage for biogas production. I mean, corn silage is regarded as a first generation fuel, meaning that this raw material could be used as food for animals or food for people. So the governments are doing more to find solutions. So our solution is, of course, to use a waste material from wheat straw in the form of briquettes. So consequently, we recommend to switch from corn silage to straw briquettes. Just a little about straw in the beginning here. Everybody knows straw, primarily wheat straw, and for us to operate it, it needs to be in bales. A bale typically weighs 150 kilos per cubic meter. Shredded straw weighs 60 to 75 kilo per cubic meter. Briquetted straw then 400 to 500 kilo per cubic meter. This will give some logistical advantage, which we will touch later, but it also gives you a very big advantage in relation to your biogas operation, which we also will touch on later here. This is some of the points we're going through. Little about agricultural residues. Craig told us how much is available in the Far East or in ASEAN countries. There's a lot available in Europe too. On which effects will briquetting do to the straw? I mean, what makes this different? And then which yields do we get from the straw? Later on, we turn to how is the process and what costs are involved. And finally, how do we operate this at the biogas plant, and some summary of advantages. But Torben, maybe you can take over a little and tell us something about straw.
Yes, thank you, Mogens, and good afternoon, everybody. Straw is a plentiful resource. Throughout Europe, we find vast quantities of cereal straw, rape straw, and it is simply sitting out there waiting for us to mobilize it and using it for anaerobic digestion, producing biogas, or perhaps advanced biofuels such as cellulosic ethanol or whatnot. The quantity here is in one paper estimated to at least 150 million tons annually, and that is a conservative estimate. But this is just to say that this is an abundant resource that is out there. We just need to be able to mobilize it, to manage it, and to digest it. Then we can simply, by means of utilizing this straw resource, replace all maize, silage, or energy crops and boost our biogas production and make AD a substantial and significant player in the energy market. We can replace virtually all natural gas use in Europe, etc., etc. You know the story. This is an abundant resource that is simply available to us, and most notably, we think it is available to us now simply because we introduced this briquetting technology, which is a 3-in-1 solution. It helps. It's a logistic solution. It is a management solution at the biogas plants, and it is a pre-treatment solution that allows us also not only to mobilize the straw, but to benefit from the biofuel potential. So next slide, Mogens, please. But in order to use it for biofuel, we know to recognize what straw is, how it is constructed. And on the scanning electron microscope, you see the very, very porous structure of straw. Straw is simply built, as you all know, to sit and stand out into the field and withstand water and pests and bacteria and fungi and enzymes and whatnot. And it's simply built very effectively, allowing the crop to grow in the field. But when we want to convert it to biogas, all those factors work against us. So we need to overcome that fundamental barrier that straw is highly hydrophobic, for instance. And we do that by our dedicated briquetting technology. After straw passes our process, it is simply in a split second compressed by means of high pressure, 1,500 bars, and a high temperature development. It is simply compressed very effectively, exploding all the pores, melting all the waxes, allowing water directly to penetrate into the deep matrix of the straw. The video we will play now displays a compact fiber under the microscope where we just add the water, boom, and you will see that this fiber, an internode fiber, simply directly absorbs the water. And that is fantastic to see. And it is exactly what we want to achieve when we wish to inject straw into a digesting. We simply need them to be hydrophilic, as we see displayed here, because once it absorbs up to 10 times its own weight in water, it has the same density as in water, and it's easily suspended in the liquid, and it's also very easily digested into biogas. So this is simply phenomenal. It solves the technical issues of using straw at industrial quantities in biogas plants. The next slide, please.
Well, here I'll just take over and show you really what's happening inside the briquetting press. If you look at this video here, this is basically with wood, but it's the same principle when you work with straw. You can see the raw material is put into the press and then distributed to two compression slides that brings the raw material in front of a piston that moves about 270 revolutions per minute. This then enters the press, and what happens inside the press is, as Torben mentioned earlier, is the straw goes into a conical die system, and the revolutions of the piston creates high pressure. And since there's a certain amount of water left in the straw, 12, 15%, you'll get a small steam explosion which destroys the straw. So meaning the mechanical movement, the high pressure and the heat then changes the straw. Which again, Torben, maybe you can tell us a little about how this works.
This is a very simple setup that illustrates that the straw, the briquetted straw, has completely rendered its properties. When we start this small video, you see that the 70 gram of briquetted straw on the left hand, and you see the same quantity, 70 grams shredded straw on the right hand, and we just add it into a bowl of water. And then we just see what happens. So the next slide. So after just 15 minutes, of course, the shredded straw resides on top of the water, not absorbing anything, and the briquetted straw has absorbed all the water in that bowl. And that is exactly what happens in a in a digester. Once we add the high density bricketed straw directly into a digester, within minutes it absorbs the water, becomes dissolved, and then digested and giving off lots of methane. So this is simply a wonderful new phenomenon, a new quality that the bricketed straw displays here, which simply allows us to use straw in vast quantities. The next slide. If I continue a little bit, in a standard agricultural biogas plant, we generally see a yield of 250 cubic meter methane per tons bricketed straw. And when we say a standard plant, we generally mean a thermophilic temperatures and a residence times about 30 to 40 days. This is not an excessive yield or underestimated. This is a robust average yield per tons of bricketed straw. In comparison, you may note that 1 tons of maize silage would give you approximately 100 or maybe 90 or thereabout cubic meter methane per tons. So, and that is of course because 1 tons of maize silage contains about 30-35% dry matter, whereas the straw contains 85-90% dry matter. So, so 1 tons of bricketed straw almost replaces 3 tons of maize silage. And based on those rough numbers, you can make your business calculation if under your specific circumstances, bricketed straw would make sense. The next slide, please. This is an illustration of if you just have a typical slurry-based biogas, maybe 100,000 tons of pig slurry, cattle slurry, whatnot, it maybe gives off an average of 2.5 million cubic meters methane. And you go on, Mogens. And if we just add 10% of bricketed straw, we simply double the output of methane for this agricultural plant. And that is, of course, significant. But you may not only add 10%, you could potentially add 50% of straw and doubling 2 or 3 more times. Then you need to do some managing and recirculation of some nutrients. But the simplest version of this is that you just add 10% of bricketed straw relative to the liquid input, or then you will at least double your biogas output, or in this case, it's calculated as methane output. So, think about it. This is actually, well, sometimes I call it a divine recipe for producing biogas. Farmers, they have all the dilute pig slurry, cattle slurry, and whatnot, and they are also in possession of the cereal straw. The combination of these 2 substrate is simply perfect. It's a perfect match. The slurry brings in water, nutrients, biological buffer. The straw brings in the dry matter, giving off all the gas, and it works beautifully. Also, adding the straw gives you a number of side benefits, of co-benefits, because it stabilizes the biogas process. Straw comes in with a very wide carbon to nitrogen ratio, while manures come in with a very low carbon to nitrogen ratio, meaning that you generally see ammonia inhibition, etc., etc. And that is simply solved by adding straw to your digester. So the biogas process is very stable, and the co-digestion aspect of this simply also increases the biogas yield, specifically from the manures and other substrates. The next slide, please.
Well, of course.
Yeah. Thumbs up. When we measure the specific methane yield, we generally do that in the laboratory settings. You know that you have half a little bottle and then you incubate and whatnot. And when we do all that, and when we test various pressures, etc., we pretty much end up with the same potential of between 300 and 350 liters per kilo volatile solids. And because the variability is very or the variability is very small here, and that's because we work at a very, very high pressure. It's around 1,500 bars. If that pressure is 1,400 bars or 1,600 bars, it really doesn't matter on the outcome. So we have a very robust and simple pre-treatment technology here that simply allows us not only to solve the logistics and the feeding in aspects, but also at the same time solving the pre-treatment aspects of the straw. So the next slide, please. We have operated all kinds of fermenters, lab scale, renters, semi-scale, and whatnot. One of the highlights here is that we operated 2 full-scale reactors in completely parallel, one alone with cat manure and one with 9% added straw briquettes. And in that scenario, we found the doubling of the biogas output and a specific yield of 351 liter methane per kilo volatile solids in this combination of cattle slurry and straw. So this is a perfect illustration of what we are talking about, and it's a perfect illustration of the potential of co-digesting various manures, other waste with cereal straw briquettes. The next slide, please. So we have talked about the actual briquetting process and what it brings to the AD industry. By means of this technology, we can mobilize the 150 million tons annually in Europe. We can add 50 or 100,000 tons or 500,000 tons to any specific plant producing biogas or cellulosic ethanol or whatnot. And this pre-treatment is a very important first step in converting the straw to a biofuel. As mentioned, we generally say that you can achieve at least 300 liter methane per kilo volatile solid in a sort of standard agricultural-based digester. But the final biogas yield is actually very dependent on the specific type of digester you are running. There are several technologies available to us that will increase this yield. And I have indicated some of those that I work with myself and implement in large industrial plants working on 300 or 400,000 tons of straw. You can include in your digester setup a hyperthermophilic unit that pre-digests the straw at 70 degrees Celsius, and you will all realize that this temperature is an optimum temperature for the hydrolytic bacteria and the fermentative bacteria, and that really helps breaking the rate limiting step down, that it is the macro molecules that need to be broken down to monomers before they can be really converted into biogas. You can work with recirculation of possible undecomposed fibers and reintroducing them up front. That helps a lot. You can work with very advanced industrial process where you have a post-treatment of the very recalcitrant organic matter, notably the lignin. So you have technologies available that really allows you to determine what biogas yield you wish to have in your specific AD project. An important point is that the total or the gross energy content is, according to all the data I have, is 19 to 20 megajoule per kilo volatile solid. And that converts directly to a gross energy content of 550 liter methane per kilo volatile solid. So that is actually the ultimate potential. And what can be realized theoretically is maybe 500 or a little less liter per kilo volatile solids. So that is potential that you can go for when you work with the larger industrial AD products. And in normal agricultural base, you can go for the 300, 350, maybe 400 liter per kilo volatile solids in gas yield. And this can be achieved, and we of course more than happy to guide on the various AD technologies that we can support you with here, and of course also with our briquetting technology. We see the briquetting technology as a key technology that allows us three things: to mobilize the straw, to manage it and to directly inject it into the digesters, to pre-treat it and to get a very, very decent biogas yield and even optimal yields in industrial plants. The next slide, please.
Yeah, and Torben, we have to move a little faster. I think, Leanne, you have to help us if we are running out of time.
No, you're still good. You've got another 7 minutes yet.
Okay, good. We still have to show you a little video from an existing plant. So.
Go ahead, Mogens.
Yeah, but here you see where we have tested this. We have tested at the University of Aarhus in Falun, where they have a reactor. We tested this for 3 or 4 years. And here's the plant. I'll show you a more large plant later, but what we did here was about 800 kilos per hour plant and running it for 3 or 4 days. All this is documented. Several PhD students and professors have been working on this, and papers are available. Here are some of them. We will not go too much into detail on this. But let's get a little into the process so you understand what that involves. It does not only involve a briquetting press. What's important using especially wheat straw and other types of straw is the moisture of the straw. This is key to operating a briquetting plant, and it should be around or below 15%. You need to shred, mill, and clean the straw. And here you see a straw shredder where we shred the straw from, or take the bales apart, remove the strings, and then most importantly, we remove stones. So we have a stone trap. All bales are full of impurities and many stones. Afterwards, we enter the hammer mill where we get the straw down to 20 to 30 millimeter length, where it passes through a cyclone filter and into a mixer, kind of a buffer mixer, which is some kind of a silo. You cannot put straw into a normal silo. It has to be moved all the time. If the straw contains sand or small impurities, we can remove that. It's important to remove all these things. Part of them, big particles before the hammer mill, and small particles also before the briquetting press. Sand and stones and so on are high wear on the press, so we prefer not to see that. But this is a typical operation of a straw plant. Just to give you some figures, the most important thing or cost is power. So use about 75 to 100 kilowatt per ton of briquettes produced. Labor, I write here 1/4 of a person to 1 person per shift. It depends on the size. If you're operating 5 presses, you don't need much more people than operating 1. Maintenance costs, spare parts are of course an item which will depend on the quality of the straw. If the straw is clean, then the whole operation, depending on the cost of local labor and power, will be about 25 to 30 euro per ton. We'll show you an example from the island of Sheppey, where we have installed a briquetting plant together with a new biogas plant. This plant uses 15,000 ton of silage, 6,000 ton of poultry manure, 6,000 ton of fruit waste, and then 6,000 ton of straw briquettes. Of course, the straw briquettes has a lot higher dry value or volume than some of the other parts. Some pictures, threading operation, filter, mixer, and so on, but I think it's better for you to see this on a video. So we should be able to show that here. Here you see the Sheppey plant. It was all new, so it probably looks different today. It was started late last year, and we have been operating the briquetting plant since then. Again, this is a 3D view of the plant. They have plenty of straw on the island. This is kept outside. Here they load the bales onto the pre-shredder or the shredder. They remove the strings, and then the straw is threaded in the shredder. This is a shredder seen from the other side. This is working on demand. The plant will call straw when it's available. Here's a stone trap. Most importantly, we remove stones before we get into the hammer mill, and then from the hammer mill through the filter into the side or the mixer. The mixer, as I said, is a silo. In case the threading operation stops, and the briquetting presses will move the same. If the briquetting press should stop for a short while, the rest of the operation can move. Here we have two presses. On Sheppey, they run 3.5 ton. In total, we normally guarantee 1.5 tons, so they do well. What you can see here is just water vapor from the press. And the briquettes are then let out on cooling lines. It's a both transport and cooling. And here they fall down. The briquettes are soft. We can make them hard or soft, but for biogas operation, it's right to have a soft briquette. So let's stop here and move on to the last couple of slides. Well, what they do here, they introduce the briquettes in a big mixer. Mixes, in fact, all different kinds of raw material together, and then pump it in together with silage into the biogas reactors. Let's just sum up some of the advantages. I think we are very close to running out of time, but as we told you earlier, it's a second generation technology. The tendency that we'll move away from this, and this will move away from first generation and into second generation. So this is a good aspect. The straw absorbs 7 to 10 times more than threaded straw. We have potential customers that have tried to introduce threaded straw into the digester. This is not possible because physically it will not absorb, and it cannot be introduced into the reactor. Again, as mentioned, we generate 250 liters of methane per ton of straw. And it gives you a logistical advantages. If you have the briquetting operations away from your biogas plant, well, it's not very expensive to move and easy to move around. They are dense and easy to handle. We have patented this and documented this through a cooperation with the University of Denmark in Aarhus in Denmark. And then finally, as mentioned in the beginning, there's plenty of straw.